Let's just summarize what you were supposed to get out of all of this. Because sometimes, and they actually say it on here, which I kind of like, there's a disease known as formula fixation. And you do that, right? You just like write down like, this is page, not homework, right? So the point that I want you to get out of this is that it's not just about that. It's about kind of understanding really what's going on. And we have this thing, and it's called momentum, and we use the letter P for it. And you take mass and you multiply it by velocity. And it is a vector quantity because velocity is a vector, therefore momentum is a vector in a direction. The units are the units of mass times the units of velocity, which are kilograms times meters per second. Okay, so it's like a weird thing, kilogram meters per second, and sometimes you'll see a Newton second. It's the same thing. But neither one of these have like their own special name. Like energy has right momentum anything. It's just a kilogram meters per second, and it's kind of but what like for number 3 on the first page, when it says complete descriptions of the momentum, really you need to give it a direction as well. And sometimes we just say positive is a direction, and sometimes we have to be really specific and say right or west or so momentum was the kind of the first idea here. And then the second thing that you talk about is something called impulse. Okay, impulse is when you have a change in momentum. And when you have a change in momentum, in order to have a change in momentum, you have to experience a force over some amount of time. In order to experience a change in velocity, you have to have an acceleration. And in order to have an acceleration, you have to have a force, right? And so they give you this relationship where if you want to know what the force is, you can take the change in momentum and divide it by time. And that really does make sense, right? Because change in momentum is final momentum minus initial momentum. Anytime we have a delta of any quantity, it's always going to be that final of that quantity minus initial, right? So final momentum is mv final, and initial momentum is mv initial, right? And if I were to, I know this is crazy, factor out an m here, I would get m times v final minus v initial over time, which is ma, net force equals momentum. So the second law, the most important thing you'll ever learn ever. Okay, force equals mass times this, which is this impulse momentum theory, as they call it, theorem, is not like a fancy new thing. It's Newton's second law, but written in terms of things that we're learning about right now. Okay, and when we talk about Newton's second law, and we talk about Newton's momentum as well, because when things interact with each other, they exert equal and opposite forces on one another. Okay, and that's going to come into play a lot today. So you have this equation here, okay, and that was given to you, and it might have been given to you in like a slightly different form. Sometimes you'll see it as delta P equals F T or F delta T or whatever. All I did was multiply by time, and they're exactly the same. But there is a relationship between the force that's applied over some amount of time and how that changes your momentum from final stage. And then, for whatever reason, they have this word that they call impulse, which is not anything except change in momentum. It's not like, oh, it's a slightly different concept or it's a little bit different unit or anything like that. These two things, impulse, which they use I for, and delta P, change in momentum, are the exact same thing. Okay, so what you have to understand is that every once in a while in this class, there are vocabulary terms that you have to actually know, right? So on a test or on a web assignment, when it says what is the impulse, you have to be able to figure it out, either by finding delta P using this relationship, or by finding delta P using the fact that it is literally final momentum minus initial momentum. Okay, and so I don't know why they have these two different variables here. So that's kind of a recap. Now, the homework. And actually, number 8 is like a summary of what I just said. In a collision, an object experiences a force acting for a certain amount of time, and which is known. And actually, number 8 is like a summary of what I just said. In a collision, an object experiences a force acting for a certain amount of time, and which is known as an impulse. It serves to change the momentum of the object. The end. That's everything that I just said. Okay, so when in doubt, go back and read number 8, impulse and momentum. Okay. So let's go back to the brain twister. Sorry. I wanted to make sure we're all kind of on the same page before we actually do the problem. So the brain twister says kilogram is at rest. So I'm going to just start writing down the things I know. That's initial velocity. Right? The initial velocity of it is 0, and it has a mass of 0.1 kilograms. It encounters a force of 20 newtons for 0.2 seconds that sets it into motion. Then, for 2 seconds, it has a 0.4 newton resistive force. And then, for 0.05 seconds, it has a 24 newton force in the direction of motion. What is the final velocity of the hockey puck? Okay, well, each one of those is an impulse, but they're like different forces over different amounts of time. Right? So what I can do is I can figure out the change in momentum and then just add all those momentum changes together to get the net change in momentum of the object. So the first force is 20 newtons for 2.2 seconds. So it's going to make that change in momentum. And then the second force is resistive, and it's 0.4 for 2 seconds. And then the next force is 24 positive for 0.05 seconds. So you can get the change in momentum total from the very beginning to the very end, and that equals 4.4.
And you're subtracting the 0.4 from the 4 times
because it's resistance, yeah. And force is a vector, so that's the direction. So then I can say, okay, well I've got 4.4, and that is equal to the impulse, which is equal to delta P, change in momentum. Okay? So whatever I got for all of this, all of the forces times added together, 4.4 is equal to my final momentum minus my initial momentum. Okay, where do you think 4.4? Did I do it wrong? All these added together? Oh. And then I set that equal to the actual change in momentum, final momentum minus initial momentum. And the initial momentum, something not moving, 0 momentum. And so my mass is 0.1. So my final velocity is 44. So if you have more questions, fine for you to ask, or you can come and talk to me later, or you can come look at this later, or whatever you have to do. But let's move on. Let's get out our notes. So today we're gonna take some notes, and then we're gonna do some whiteboard activities, and then you're getting the homework because Thursday is the day we're gonna do the testing for your cars. Your car write-up will be due on next Friday, like the 12th or something like that. Next Friday. And next Friday, and it's short. And there's on my website, there's a link, a document that's called Great Car Vehicle Write-Up. And it tells you the point breakdown. It's worth 50 points on a test. And it tells you what I want you to say. Okay, so that's due next Friday. Yep. That will be in the test section. So then the actual results from your car will go into the lab. So as far as review goes, we're not going to have a lot of time to review for your final. So next Monday, we're going to review what we're learning today. And then next Tuesday, you're going to have a quiz on that. Okay, short-ish. The stuff we're learning is probably the easiest units that we'll learn all year, I think. And the quiz will be worth, 70 points as opposed to the 100 that the test is usually worth. And then we'll have one block day and one regular day to review for the final. So block day and one regular day to review for the final. So I will eventually put up an optional, totally optional for no points kind of web that you can just use for reference. You can also look at your old web assignments. Already on my website is a copy of the first 3 exams that we've taken. They're already up there. So the last exam that we've taken, we have to wait until everyone takes it before I put it up on the website. But the other ones, if you like don't have yours or you lost it or whatever, if you want to review the old exams, then please feel free to start doing that now. So in case you didn't pick up on what I was saying before, we're learning everything that we need to learn for this unit today. Then you're going to practice it, and then we're going to review it on Monday, and then you're going to take a quiz on it. So what that means is the things that come out of my mouth are really important, and you should listen and pay attention and ask questions. And it has to do with momentum. So we're still on the momentum unit, and you've already learned a lot of the hard stuff, which is how do you calculate momentum, and how do you calculate that an object experiences when it has a change in momentum. Today we're going to talk about when you are dealing with a system, and the word system is in itself a tricky thing to think about, a system of more than one object that is interacting, that are interacting, is are interacting. And in this case, and in all of our cases, we'll only really deal with two objects interacting. And what I mean by interacting is almost always a collision, which is exciting, things colliding, okay? And when things collide in a system of objects, momentum is unchanged. The total momentum of the whole system is unchanged. Now, the tricky part about this is when I say system. What I mean is, if we're talking about these two carts here, it's unchanged. Anyway, so you're talking about these two carts here. If they are my system, then they are the only two objects in the universe, according to my calculation. Okay, they're not interacting with anything else. There is no friction. Nothing else in the whole world is acting on these objects except themselves. Okay, and the reason that that's important is because if you look at the force and momentum equation, that force is equal to change in momentum over time, or impulse over time. If we talk about the total momentum remaining unchanged, then the delta P is what? 0, which means the force is what? 0. Okay, and if that's true, if the net force acting on a system is 0, that means that they're only interacting with each other. Like, for example, if these two things collide, if they collide with one another, the independent motion of an individual one of these changes. The momentum of this car will change, and the momentum of this car will change, but the total momentum of the two cars added together will not change. Okay, and that's because when they collide, during the time that they're colliding, Newton's third law applies. They're experiencing equal and opposite forces. So each one experiences an impulse. Each individual car or object experiences an impulse. As a combination, they're equal and opposite impulses, or equal and opposite forces. Okay, because of Newton's third law. For every force, there's an equal and opposite force. So this one hits this one, and this one pushes back to the same force on this one. Okay, so with whatever forward force this one is exerting on this one, this is exerting a resistive force back on this one. Okay, and so what that means is the net force on this system right now is 0. Okay, the net force on this system, I swear, is 0. Does it go somewhere? Okay, and yeah, of course, in reality, like all sorts of crazy things happen, and we have to deal with them. But the net force, okay, which means that the momentum doesn't change, and that is the topic of conversation today. And when we say that the momentum doesn't change, what we mean is that the total initial momentum equals the total final momentum. And that's true of combinations of 2 objects, of 3, of 7. That's true no matter how many objects are interacting with one another. You just add up the momentum of everything, and it's always going to be the same. Assuming no net force, which is a pretty good thing. This has a name. When we not change energy initial equals energy final. What is the word that we use? Constant, true, not wrong. It starts with conservation. Yeah, conservation of. Now, here's the thing. Momentum is not always conserved. This is not like a fundamental law of nature, the way conservation of energy is. Conservation of energy is always true, no matter what. You cannot ever tell me the conservation of energy is not true. You can't. There are circumstances in which momentum is not conserved. And we don't really feel that, but there are. And so this is not like a fundamental law of like the whole universe, but it's true a lot, and it's true in collision. Okay, and so that's kind of what we're going to talk about. So momentum is momentum. So when we talk about interaction, we have different types of interactions between objects. We label them. And we label them for various reasons, but mostly just so you can kind of get a sense for what is happening in different scenarios, okay, today. And the first one is when you have two objects that are interacting and that explode, okay? Now, an explosion sounds really exciting, like everything's going in all directions, and it's kind of true. Right? Momentum is conserved in explosions. And if you think of universe and how it began, right? Things started kind of all together. And then, yeah, we don't necessarily say that it exploded, but things definitely now are going in all various directions. Right? Things started together, closer together, and now we're going in every which way. That's a conservation of momentum problem with a very, very large number of objects. But it's true. So if we consider the universe as our system, momentum is conserved from beginning to end. But most explosions are not that exciting or are really difficult to handle. Like if I say, let's do a conservation of momentum problem, and you have to deal with fireworks, right? That's a lot of different little things going in all which way, right? 3 dimensions and all that stuff. So a little bit less exciting. Okay? An explosion really just means that two things start together and then they're not together anymore. So this is like anyone. One day and I'm stealing it. Okay. Speaking of the camera, I'm like, I know. It's like all right. So you've got these two cards, right? This is an explosion. The two cards are starting together. Okay? And then, watch this. It's like magic. Ready? Wow. Now they're not. They just exploded. So, here's how it goes. There's a spring-loaded thing in here. So there's energy stored, right? We have stored energy. Very good. Potential energy is stored. And then, that energy is released, and there's an explosion. Momentum is conserved. About momentum of the system, it's 0. But they're both moving after the explosion, right? Opposite directions, and momentum is a vector. Therefore, those two things, positive, negative, can cancel each other out. Okay, so that's now you have an explosion where they're moving to start with, and then they explode in opposite directions. Okay, so that it's not like they have to start at rest in order to be something that's exploding, right? For example, fireworks. You launch something up into the air, it's flying through the air, and then it explodes. Right? That's still an explosion, momentum is still conserved. Okay, it's just that the initial momentum is not conserved. Okay, so type 1 is an explosion. And for all of these, momentum is conserved. Okay, so I'm not going to specifically write down momentum is conserved. I'm not going to define. I have no words. They start together and then they end apart. The next type of interaction we're going to call elastic. It's an elastic collision.
One where they like stick together.
I'll tell you about that. It is not. Elastic collision. And actually, let's talk about the bouncy ball lab for a second. Okay, let's talk about the bouncy ball lab. The bouncy ball lab really belongs in this unit, but I knew we wouldn't have time to do it. So when you elastic collision, and actually, let's talk about the bouncy ball lab for a second. Okay, let's talk about the bouncy ball lab. The bouncy ball lab really belongs in this unit, but I knew we wouldn't have time to do it. So when you have something that's an elastic collision, remember the graph we made about the amount of energy that was lost each time the ball bounced? That what you were measuring was the elasticity of the collision of the ball with the ground. If it were perfectly elastic, if it were truly an elastic collision with the ground, then it would have returned exactly to the same height. It would have lost no energy due to that heat or deformation or whatever, squishing something off. No energy would have been lost. That's what elastic means. Elasticity, if something is perfectly elastic, it loses no energy. These are called happy and sad balls, and they look the same. But if I bounce them on the ground, something different happens. Wasn't that awesome? Now, if you're watching the video, you can find the happy and sad balls right up here, and you can do it yourself. But the difference was one of them bounced and the other one didn't, right? One of them has elasticity and the other one does not. It has no elasticity. Okay, it's inelastic. So in an elastic collision, there is zero energy lost. Zero energy is lost due to heat or thermal or whatever. And when we define it, we say that kinetic energy is conserved. We can also say that there is no work done by friction or no thermal energy is lost. Okay, kinetic energy is conserved. Now, when things touch each other intrinsically, they lose energy. Okay, so really, truly, the only true examples of elastic collisions are ones where things don't actually touch. Can you give me an example of that? Magnet. Oh, I wonder if these cars have magnets in them. Oh, I think they do. Interesting. Okay, so here's a car. It's kind of at rest. Here comes another one. They didn't touch. That was elastic. Okay, that was elastic. Because anytime two objects interact and touch each other, then you've got this heat loss. Okay, a little bit. Now, sometimes we approximate them. We say, like when you play pool, anytime you play pool, it's very much like an elastic collision. Okay, anytime where you have things that don't squish very much, okay, like billiard balls, it's very close to being elastic. But there's still energy loss. The other type of interaction that allows things to collide without touching is when you have protons or things that are charged particles interacting. They can kind of like whiz by each other without ever touching, right? And they experience equal and opposite forces, but they never actually contact one another. So that's elastic. Now, the other type, if you can imagine, is anything that's not elastic. That's inelastic. Okay? And an inelastic collision is actually defined as not elastic. It's anything that does not conserves kinetic energy. So like every real that's inelastic because they touch. Okay? That's inelastic. And they're both going in the same direction, but one's going faster. That's inelastic. That was very, very inelastic. Okay? So if you give me like examples of things colliding, then that's inelastic. Okay? And then the last type is called perfectly inelastic. And perfectly inelastic is what it is. So if you have sure. Anytime you have a collision where things stick together. So in this case, they stick together post collision, right? Stick together post collision. Okay, give me an example of that, of when that happens a lot. Yeah. Huh? Okay, sure. Right, like a bear hug. I was thinking like football, right? Where when you tackle somebody, you generally like stay with them. Like now we're gonna move together for a while, right? And the bear hug is kind of like that. Like if you're moving and that person like continues to move as you hug them. I mean, maybe. But so yes.
What's the main difference between number 3 and number 4?
Inelastic is when they don't, is any type of collision that is not elastic. Perfectly inelastic is like a subset of inelastic, where it is inelastic and also they stick together. Okay, so it's like, these are the two extremes. Okay, perfectly inelastic is the ground and doesn't bounce at all. Okay, whereas inelastic is like when you did the lab and they were bouncing on the ground, but they didn't return to the same height that they did the first bounce. And then elastic is if they magically were to return to the same height. So it's perfection. So it was like a really ideal situation. If we were done before, it's like they have to stick together. Yeah, stick together. So perfectly inelastic is when they stick together. So most collisions in this world are just regular inelastic. Some of them are perfectly inelastic. Some of them are elastic. Okay, but most of the ones that you'll encounter or whatever will be. And it's not about like memorizing the terms so much as if I say something like two people collide in a perfectly inelastic collision, then you have to recognize that that means that now after the collision they're like moving together. They're one object. Okay. Okay, so let's do some examples of calculations, ways that you can handle a situation like this. Let's say that you are an astronaut. You're in space, you're doing a spacewalk, and you are fixing your space shuttle. Disaster strikes, and you become untethered from your space station, and it's too far away. I would say normally your space suit has a small propulsion system, which would propel you towards So let's say you don't have that. All you have is your tool bag. You're fixing whatever. So you what? You throw it back in the opposite direction. Okay, let's say you're just gonna throw the whole thing. Okay, because in the end, it's just as good to throw all one at a time or all of them. You could change directions. That's true. You're right. So just in case you like miss or whatever, you want to keep like half of it. Let's just say that we want to do one calculation. Okay, so you're here with your tool bag, and your space station is like 100 meters that way. I know it's really far. So immediately you recognize that in order to make yourself go one way, you have to throw something the other way. Remember when we talked about how rockets work? It's exactly the same thing, right? You are like kind of and that was Newton's third law that we learned about. And now we're talking about conservation of momentum. They are not different. Conservation of momentum and Newton's third law are exactly the same thing. Okay, so because I want to have an explosion where I'm at rest and I throw my tool bag one way and then I move the other way, that's an explosion, right? I start with zero momentum and then you have two objects that are moving in opposite directions. Now, how do I take information from this and actually come up with like a true calculation? Okay, and the way to do it is, first of all, we need numbers. Okay, so let's say that mass of me, 55 kilograms, and let's say that my the mass of the tool bag is 8. And let's say I'm pretty strong. So I can give the velocity to the tool bag 60. I'll go 60. That's still pretty good. So my question for you is, how fast will I now move after this interaction, right? After whatever happens. And the way that you approach a conservation of momentum problem is to figure out what is the momentum before the interaction and what is the momentum after, and then equate them, set them equal to each other. That is why we understand what conservation of momentum is. So the total momentum before is equal to the total momentum after. So let's just assume that I start from rest. So what is the momentum before the zero? Okay. Now, we have two objects after, hopefully, that have momentum, right? And so we have to, the total momentum will be my momentum plus the momentum of the tools, right? But one of them will be a negative momentum because it will be going in what we can call the negative direction, right? So which one do you want to give a negative direction? Okay, so let's put the positive one first because I like to make it pretty that way. So it'll be the mass of me times the velocity of me, minus the mass of the tools times the velocity of the tools. Momentum of, this is total momentum, my momentum plus the negative momentum of the tools. Does that make sense? Does the minus make sense to everybody? Okay. Now I just plug in numbers. 0 equals 55 times my velocity minus 8 times 60. And then somebody with a calculator will tell me that the answer is 2.32 meters per second. Questions about this example? Mostly, except it's not always 0 on this side. Yeah. That's the best thing. All right, let's do another example. Let's that you are standing on a skateboard. Okay, skateboard. And the total mass of you and the skateboard is 60 kilograms. And I throw a bowling ball at you. You really have to ask that. Throw it. Yeah. Bowling ball. And the bowling ball has a mass of 7 kilograms.
What is the bowling ball when you left?
Thank you. I was going to say that. Okay. I give the bowling ball a velocity of 10 meters. And you catch it.
Without breaking.
You catch it. And you maintain your balance and you stay on the skate. What happens? You move, you're propelled backwards, right? You are propelled backwards. So,
Are you already moving?
you're at rest. Yeah. Let's test that. Caught it. You're all good. Everything's fine. The question is asked, are you going after you catch the bowling ball? What type of interaction is this? Perfectly inelastic. Now, there's no Velcro, right? There's no like glue, but you and the bowling ball become.
Is this assuming that you like stay on the board?
Yeah, you and the bowling ball become essentially one object, right? You move together as one, right? You become one with the bowling ball, and so that is the definition of a perfectly inelastic collision. Which means that if I had asked you instead, what is the velocity of the bowling ball after the collision? That's the same question, right? You're both moving velocity after the interaction. So, same kind of problem. It's still initial equals final momentum. So before the interaction, what has momentum? The bowling ball. Okay? The bowling ball has the momentum of the mass of the ball times the velocity of the ball. You don't have any momentum to start with. So the total momentum of the system is just the momentum of the bowling ball. Okay. Now how about after the interaction? Yeah, so the way it works in my mind is that I consider now it's still just one object. It's you bowling ball object. So now it's like it's a mass times velocity to get a momentum, but the mass is the mass of you plus the mass of the ball. Does that make sense? It's more of like do I want to factor or not factor, right? Or you could do the mass of you times your velocity plus the mass of the ball times the ball's velocity, but they're the same, right? So then you just factor out the velocity.
So does this only happen in perfectly inelastic instances when you use like the massive?
When you add the masses together? Yeah. Yes. If they start to move together as one, that is perfectly inelastic, and therefore that's the only time we can add this mass. Okay, so let's just put in the numbers first. So then it's 7 times 10 equals 67. What did you say? 1.4. Oh, 4. So that's how fast you're going after the collision. Not super fast. That's not that fast. Yeah, really, you'd probably fall off, but I understand.
Maybe you were like really low down.
Maybe. You're underneath.
You're like sitting on it.
Okay, let's do one more quick example. Okay, let's do an example where you're you go to a carnival and you
Evil Concord who comes around.
and you decide that you want to do the bumper car. Okay, so this is you. This is me. Hot date. And you are the date's not going so well. So you decide you're going to you're gonna hit your hot date with your bumper car head on fast. So let's say that you are going at your date, so we'll call this the initial velocity of you.
Are you wearing your seatbelt?
Huh?
You're wearing your seatbelt?
Of course, absolutely. let's say that you're going 12 meters per second, and your date, the initial date, is going 14 meters per second. And let's say that your mass is 60 kilograms, and the mass of your date is 100 kilograms.
Wait, question. How does this work?
Just go with it. She's a football player.
I don't know how much
Okay. All right. So, after the collision, you bounce off and go the other direction. So the final velocity of you, let's say, is 2 meters. Not necessarily. It depends on how elastic it is. It's definitely not perfectly elastic, okay, but it really depends on what else is happening. So yeah, I guess let's give it a little bit more. You're right, a little more. 7. We'll call it 7. And the question is, with what velocity? What is the final velocity of your gate? And I put an arrow this way, but I don't actually know that to be true. Right? When you collide, two objects collide, it's either like this, or like this, or like this. Right? You don't know until you do the numbers whether or not this final velocity is to the right or to the left. So really, I should put like I don't know which way it is. Okay? So what we want to do, and what you always want to do with vectors, is choose a direction that's positive. So which way do you want to make positive? Left is positive. All right. Right. I like that you guys want to do something a little different and make left positive, but then everyone does that. So that way is positive. Which means that the initial momentum of you is positive and the initial momentum of your date is negative. Okay? So the total initial momentum is going to equal the total final momentum. But the total initial momentum is now the sum of your momentum plus your date's momentum. So it would be the mass of you times your initial velocity. Well, you're adding as vectors, so you will be subtracting. But then we're summing vectors, therefore it will be minus the mass of your date times the initial velocity. Most of this equation is subscripts. It looks complicated, but it's mostly because I'm writing out the whole word, U and D. Now, after the collision, we know the total momentum will be your momentum, which is negative for sure, plus the momentum of your date, which we don't know. Right? The sign of our answer will tell us. So now on the other side, it will be date minus U. Well, or we could just say, we could leave it in the same order, and we could say negative mass of U times VFU plus mass of the date times the date final velocity. And I put a plus because I don't know what the sign will be. The answer will come out as positive if it's positive and negative if it's negative. Now we have all these numbers. So 60 times 12 minus 100 times 14 equals negative 60 times plus 100 times VF. Don't tell me what it is. I can do it in my head. Okay. Oh, you forgot to add the 60 times 7. I did it. I just did it wrong. Okay, so 60 times 12 minus 100 times 14 is what? Okay.
And then plus 60 times 7 is negative 5.
So it's negative 5. Yeah, I did that right, I think, because this is 60 times 7 is.
Oh, I didn't say that time. Yeah, I got what you got.
So I did it right?
Yeah.
Winner.
Negative 2.
Negative 2.6?
Yeah.
Yay, go me. Okay, so that's the answer, and now you know that the date keeps going this way, right? So it's a collision where you're coming at each other, and then you end up both going that way. Okay?
Yeah. Or you're not together.
You're not together, right? Because you're moving at 7, and your date is moving at 2.6. So you have different speeds. So it's just regular inelastic, things are just colliding, and that's all. Okay? Okay, so now what we're going to do is we're going to practice a couple more of these types of problems on whiteboards. Okay, so everybody grab a whiteboard, and I'll give you a couple problems.